Now that we've covered the circuit quantity concepts of current, voltage, resistance, and power, we're ready to move on to DC circuit analysis. And in this course, initially we're going to start off with DC steady-state circuit analysis. All right, and this is a case where current and voltage throughout the circuit do not change with time. Eventually, in the class, we're going to be looking at systems where the current and voltage do change with time, or parameters of the system do change with time, and those are called dynamic systems. We will get to that in the second module of the course, but before we do that, we're going to need to do the steady state analysis. And the reason we're going to do the steady state analysis portion is because the concepts that we learn in the steady state analysis will apply almost directly to the dynamic system analysis that we will perform later. But before we do that, we have to review the concept of an open circuit and a closed circuit. Okay, so the diagram on the left shows us an open circuit. All right, and this open circuit consists of a voltage supply. And remember that a voltage supply is going to do work to separate charges. And we're going to have a high side right here where we're going to accumulate positive charge, an excess of positive charge, and a low side where there's an accumulation of an excess of negative charge. Because of this, we're going to establish an electric field around the elements around this resistive element right here. So the power supply, the voltage supply, creates this electric field, but because there's this switch right here, and the switch is open, even though there's an electric field presence, there's no conductor, there's no path through which charges that want to move from the area of excess positive charge, they can't get away from that area to recombine or to negate the negative charges that are built up on the low side of the power supply. So since there's no path for those charges to move, there's no current flow in the circuit, and since there's no current, we call this an open circuit. Now if we close that circuit, this voltage supply is going to continue to do work to make sure that there are an excess of positive charges on this side of the circuit and an excess of negative charges on the low side of the circuit. But since the circuit is closed and there's a resistive path right here through which those charges can move, we do have a current flow. So when we have a current flow possible from the high side of the voltage supply to the low side of the voltage supply, we have a closed circuit, and this is the case that's most interesting to us right now. And that's what's going to give us our steady state current and voltage through the circuit. Okay. We also need to touch on the concepts of ideal power supplies. In this class, initially we're going to be using a number of abstractions. Actually, all throughout our circuit analysis we're going to be using this, this principle of abstraction. And this principle of abstraction, we're going to represent elements and behaviors using these ideal elements. Okay, so an ideal voltage supply is represented by this symbol right here, the schematic symbol in here, and it's going to maintain a specified potential difference across its terminals irrespective of how much current is required to do that. Right, so this is going to have a fixed voltage, a fixed potential difference across the terminals where the positive side, the plus sign, indicates the accumulation of more positive charges relative to the lower side, the negative sign side of the voltage supply. So the analogy for an ideal voltage supply in using the water analogy is that of a constant pressure pump. It's always going to maintain a constant pressure across it, irrespective of how much water or how much liquid it has to move and how quickly it has to move that liquid. All right, so or fluid. So ideal voltage supply always maintains a specified potential difference across its terminals irrespective of how much current is supplied. And that's in contrast to an ideal current supply. An ideal current supply is given by this symbol right here where the arrow points in the direction of conventional current, or the direction that positive charges are going to tend to move. All right. So an ideal current supply provides a constant flow of current irrespective of the voltage or the potential difference across its terminals. And the analogy for this is a constant flow pump. It's always going to provide a specific mass flow rate of fluid through it irrespective of the pressure difference across the pump. So it's always going to make sure that the flow is moving, whereas the voltage supply always makes sure that there's a potential difference or a pressure difference using the water analogy. Now, using these abstractions and using these ideal supplies can get us into trouble a little bit if we don't recognize the limitations. So we need to look at some of the limitations of the voltage supply. So the ideal voltage supply, again, recall, is going to maintain a specified potential difference across its terminals, or a specified voltage across its terminals, irrespective of how much current is needed. So where we get into trouble with this idealization is if we have a closed circuit wherein there's no resistance. So in our circuit analogy, or in our circuit analysis, when we're looking at our circuit diagrams, anything that's a wire that doesn't explicitly have the resistor symbol, doesn't use that symbol, we're going to assume that those wires have zero resistance to it. So this is a voltage supply connected to a circuit that has zero resistance. All right, we're going to maintain a constant voltage supply and a constant potential difference across the terminals with a resistance of 0. All right, so V is a constant value, R is 0, and from Ohm's law we know that V equals IR. If we want to determine how much current is flowing through that wire, that zero resistance wire, and remember that this is an abstraction because real wires do have some small amount of resistance to them. But for all intents and purposes, we're going to model them as having zero resistance. So if we want to determine the current, we can rearrange Ohm's law and solve for current. So I is equal to the voltage divided by the resistance. Right? And when we do that, we see that since the voltage is a constant value and the resistance is 0, this is going to tend towards a very large number, or a nearly infinite value. Okay? And of course, voltage and current tell us about how much power is delivered to the system. So this would imply that we have to the voltage supply has to supply an infinite amount of power, an infinite amount of energy into, an infinite amount of power to the system, which is physically impractical, physically not realizable. So this is a consequence of this idealization. We will worry about how to handle non-ideal voltage supplies later on in the class. For the current supply, or the ideal current supply, we run into a similar issue with an open circuit. So remember that an ideal current supply is going to provide a motion of positive charges in the direction that the arrow states. All right, and again, now that we have an open circuit, our resistance is nearly infinite. All right, since our resistance is nearly infinite, again, we can determine what the potential difference developed across that current supply is going to be. All right, so using Ohm's law, again, V is equal to IR. I is going to be a constant value, and our resistance is infinite, so the voltage is going to tend towards a very large value across the terminals here, which makes sense. We're continuously moving positive charges from this terminal up to this terminal, so the potential difference, we're going to add more and more positive charges up here. All right, and if we keep on doing that, we're eventually going to accumulate a large amount of positive charge relative to this side of the current supply. So it's just going to keep building up and building up. And again, that's going to require an infinite amount of power to make that happen, which again is physically not realizable. All right, so with that, we also know Ohm's law. All right, and we know that there's through linear devices. We will talk about some nonlinear devices, but for these things that we're calling resistors, right now we're saying that they're given by Ohm's law, and this is an abstraction, of course. The abstraction doesn't account for the fact that resistance can change with temperature. It doesn't account for the fact that there's heating involved when we dissipate power through a resistive element, when we have a potential difference in current through it, we're assuming that this resistance value, at least right now, does not change as there's a current flow and a potential difference developed across it. All right, so this is yet another abstraction that we're using. Okay. Now, along with that, we're going to need to know how to use Kirchhoff's current laws. We're going to need the concept of Kirchhoff's current laws. Kirchhoff's laws, which are comprised of Kirchhoff's current law and Kirchhoff's voltage law. All right, so these two laws are incredibly important in this class because we're going to use them for all of our circuit analysis for the rest of the semester. All right, Kirchhoff's current law is a statement of conservation of electrical charge. So basically what Kirchhoff's current law says is that if we have current flowing all in the same direction into one place, that can't happen. All right, we can't accumulate charge at this junction right here. All right, so the sum of all of the currents flowing into an electrical junction or an electrical node is equal to the sum of all of the currents flowing out of the node. So in this case, where we have here the sum of all of the currents into a node has to be identically 0. So that means one of these currents, I1, I2, or I3, actually, even though we've drawn the arrows to be going towards this point, at least one of them has to be going away from it, if we're going to assume that these are all positive values. Excuse me, if we're going to assume that one of these currents will have to be negative so that it's actually leaving that node, not going into it. Kirchhoff's voltage law is a statement of the conservation of energy. Remember that voltage tells us about the work required to move a charge, and remember from statics and dynamics that work and energy are the same thing. All right, so Kirchhoff's voltage law tells us that the sum of all the electrical potential differences, or all of the voltages around all of the elements in a closed circuit loop, must be identically 0. So in this example right here, we have our voltage supply that's at a set value, and that's providing energy to the circuit. We're providing energy to move charges against an electric field. All right, and since this is a closed circuit, we're going to have current flow from the high potential side back down to the low potential side. All right, in this case, as the current moves from this side of the resistor down to this side of the resistor, we have a drop in the potential energy of those positive charges. Since we have a drop in the potential energy, that corresponds to a voltage decrease or a potential energy decrease. So we're gaining energy from here to here, and we're losing energy from this point down through the resistor. And those two have to sum up to 0 to satisfy the conservation of energy, or Kirchhoff's voltage law. Okay, now for simple circuit analysis, what we can do is we can use the concepts of Kirchhoff's current law and Kirchhoff's voltage law to combine resistors into equivalent resistances. So I know you've probably seen this from previous physics courses, and we're going to show you how that comes about. So to determine the voltage and current through all these circuit components, we're going to use the concepts of Kirchhoff's current law and Kirchhoff's voltage law to derive these equivalent resistances. All right, and we'll come up with some familiar things here. I'm sure you've all heard that resistors in series, the equivalent resistance of resistors in series is going to be the sum of all of the resistive elements that are in series with each other, and this is why it comes about. The first thing that we have to define is our elements that are in series with each other. So resistors are connected or said to be in series if they see the same current, all right, if they carry the same current. So in this example right here, since this is a closed circuit, we have a voltage supply right here. Current is going to move through both resistor 1 and resistor 2. Since there's no other path for current to possibly go, the same amount of current has to go through resistor 1 as that goes through resistor 2. So since they have the same current through them, they're in series, and what we can do is apply Kirchhoff's voltage law around the loop. So Kirchhoff's voltage law says the sum of all of the potential gains and losses in the loop have to sum to 0. All right, so we have a gain with V1 and we have a loss with resistor 2, and that should be resistor 3 right there, V3. Now what I'm going to do is I'm going to use Ohm's law. Remember that V is equal to IR, so we can remove the voltage supply is fixed. We can replace V2 and what should be V3 right here with the current through resistor 1 and the current through resistor 2. Remember that those values are the same. I is the same through each resistive element. And multiply that by the resistance of those two elements. All right, I'm going to take those to the other side of the equation and pull them out, and I get something that looks a lot like Ohm's law. V equals IR, except now R is R1 plus R2. Well, that tells us that this circuit right here is equivalent to this one right here if this resistor, the single resistor, has a value of R1 plus R2. All right, and that leads us to the conclusion that the resistance of elements that are connected in series, we can find the equivalent resistance by adding up all of the resistors that are in series with each other. So that's how it comes about. And we can also do resistors in parallel. Now, resistors in parallel, the definition of a parallel element is that parallel elements have the same potential difference or voltage developed across their terminals. All right. So before we go on to that, what I would like to make sure we do is clarify a point of confusion that I've heard many people express before. From some of your previous courses in physics, you may have heard the phrase that current takes the path of least resistance. All right, and I'm going to tell you that that's sort of a half. Well, that is true, but it may be confusing to some people. All right, so let's say we have a resistor that has 1 ohm of resistance and 3 ohms of resistance over here. So we have a 1 ohm resistor and a 3 ohm resistor. Okay. Sometimes the statement that current takes the path of least resistance is confused by people, and they say all of the current is only going to go through resistor 1. Through that 1 ohm resistor. And since it takes the path of least resistance, there's no current flow through resistor 3. Or the 3 ohm resistor. Let me make sure I do that. Okay. So that statement is not true. Current actually is going to proportionally take the path of least resistance. So we're going to have more current flowing through through that resistor, that 1 ohm resistor, than will move through that 3 ohm resistor. But current will actually move through both resistors. And the way that I like to picture this is, let's look at our water analogy. If we have a pump, all right, and our pump is pumping or increasing the pressure in this top pipe here relative to this bottom large pipe right here. Okay, and we have two elements. We have two pipes that are connecting these together. One that has one that's really wide and has a low resistance to it, and one that is a little narrower and has a little more resistance to it. And there's a pressure difference across this. So there's a delta P across here. The fluid that exists inside this pipe network, we're still going to, since there's a pressure difference here, there's still an impetus for that fluid to move from this high pressure side to the low pressure side through both tubes. All right, it's not going to only go through this one. The water or liquid's not just going to go through this one because it's larger than this one. It's going to go from the high pressure area to the low pressure area via whatever method, whatever path it can take. It's just that because this one is larger in diameter, we're going to have more liquid flowing through this one at a greater rate than we're going to have flowing through this one. And that's the same thing that's going on with our circuits here. Right? So now with that addressed, if we go back to parallel arrangement, we know that there's going to be some current through each of these resistors in this parallel configuration. So remember, parallel means that they have the same potential across their terminals. All right. To come up with the equivalent resistance for this, we're going to rely on Kirchhoff's current law. And Kirchhoff's current law tells us that at this node right here, at this point where we have two possible paths for the current to move, we have to have whatever current is going into that node or into that junction point has to be balanced by the current leaving that from that junction point through resistor 1 and resistor 2. And now I'm going to replace the currents 2 and 3 using Ohm's law with the voltage and the resistance, the statement of V over R. Remember that if we rearrange Ohm's law, we would wind up with I is equal to V over R. When we do that, we can pull out the voltage because remember the definition of parallel is that they have the same potential difference or same voltage across each of the elements, so that's the same. I'm going to factor that out, and then I'm going to rearrange a little bit. All right, and if I rearrange a little bit, remember that I over V is the same thing as 1 over R. So 1 over R equivalent is equal to 1 over the first resistor plus 1 over the second resistor. And we can extend that for however many resistors we have in parallel with each other. So for resistors connected in parallel, using this Kirchhoff's current law argument, we wind up with the familiar relation that the equivalent resistance, or 1 over the equivalent resistance of the parallel elements, is equal to the sum of all of the reciprocal, or excuse me, is equal to the reciprocal addition of all of the elements that are in parallel with each other. Okay, so with that, we're ready to tackle some circuit analysis, and we will look at some examples.